Earlier in this series, we discussed the energy analysis of a control mass, and we obtained this energy equation. This is based on the fact that the change in the total energy of a closed system is equal to the heat supplied minus the work done by the system. For an open system, however, in addition to heat and work flowing through the boundary, some mass of the working substance also flows in and out of the boundary. So for the change in energy of the fluid, we also have to account for the energies of the fluid flowing in and out. The total energy for a certain mass of a substance is given as its internal energy plus its kinetic and potential energies. So the energy of the fluid flowing in equals the internal energy of the fluid flowing in plus its kinetic and potential energies. And for the energy of the fluid flowing out, it is equal to the sum of its internal energy plus its kinetic and potential energies. Another thing we have to account for is the boundary work as a result of inflow and outflow of mass. Apart from the work done by the system on the surroundings, there's also work done on the system by the incoming fluid, because the net effect of the flow is that the incoming fluid pushes on the fluid already in the system in order to flow in. Similarly, there's work done by the system on the fluid flowing out, because the net effect is that the system pushes on the outgoing fluid in order to flow out. So the boundary work for inflow for a fixed mass of fluid equals the force multiplied by the distance through which this mass of fluid flows into our system. This force can be expressed as the pressure at the inlet multiplied by the cross-sectional area of the inlet. So the boundary work in equals the pressure multiplied by cross-sectional area multiplied by distance. Now the cross-sectional area multiplied by this distance is equal to the volume of this fixed mass of fluid. So we can write our boundary work in as the pressure at the inlet multiplied by the volume of fluid which flows into our system. And in the same way, we can write the boundary work done by the system at the exit as the pressure at the exit multiplied by the volume of fluid which flows out of our system. Now that we've considered all the sources of energy flow for a control volume, we can say that for a period of time for which a control volume is observed, the change in total energy is given as the heat added during this time plus the total energy of the fluid which flows in during this time plus the inlet boundary work done during this time minus the total energy of the fluid which flows out during this time minus the exit boundary work done and minus the work done by the system during this time. Because we're dealing with a control volume, mass is flowing in and out continuously. So we must be able to define the instantaneous change in the energy of our system, not just the change in energy after a certain period of time. To do this, we have to define a quantity called the mass flow rate, and it is simply the rate at which mass flows through our system. Consider a small opening through which some mass of fluid flows. The mass of the fluid is given as its density multiplied by its volume. And its volume is equal to the cross-sectional area of the opening through which the fluid flows, multiplied by the distance through which the fluid has flowed through this opening. So we can write the mass of this fluid as its density multiplied by the cross-sectional area of the opening multiplied by distance. And so mass flow rate, dm dt, is given as the density multiplied by A multiplied by dl dt. dl dt, which is the derivative of distance with respect to time, is the average velocity of the fluid as it enters the opening. So we can write our mass flow rate as the density multiplied by cross-sectional area multiplied by velocity. Also remember that density is the inverse of specific volume. It will be useful to use specific volume instead of density, since we use it a lot more often. So our mass flow rate equals cross-sectional area multiplied by velocity divided by specific volume. Now, going back to our change in energy. The change in total energy per unit mass becomes this. And we can write dq dt as dot q, which is the rate of heat transfer to the system. We can also write dw dt as dot w, which is the rate at which work is done by the system. For the derivative of the sum of energy inflow and inlet boundary work, we can evaluate it as the sum of these terms per unit mass multiplied by the mass flow rate. And the sum can be written as the internal energy of the fluid flowing in plus its kinetic and potential energy plus the pressure at the inlet multiplied by the volume of the fluid flowing in. We can use the thermodynamic definition of enthalpy. So the enthalpy of the fluid at the inlet is equal to its internal energy plus the pressure at the inlet multiplied by its volume. And so the sum of the energy inflow and inlet boundary work becomes the enthalpy at the inlet plus the kinetic and potential energies of the fluid flowing in. It can be written as enthalpy plus mass times the square of velocity divided by 2 plus mass times the acceleration due to gravity multiplied by the height z above a reference point. And per unit mass, this becomes the specific enthalpy plus the square of velocity divided by 2 plus acceleration due to gravity multiplied by height. So the derivative of the sum of energy inflow and inlet boundary work becomes the mass flow rate multiplied by enthalpy plus the square of velocity divided by 2 plus the acceleration due to gravity multiplied by height. Similarly, for the exit, the derivative is also the mass flow rate multiplied by enthalpy plus the square of velocity divided by 2 plus the acceleration due to gravity multiplied by height. But this time we're using the exit parameters. For simplicity, I'll just use the subscripts I and E to denote inlet and exit. So after obtaining all of these, we can write the rate of change of energy for our system as the rate of heat transfer to the system plus the mass flow rate at the inlet into enthalpy at the inlet plus the square of velocity at the inlet divided by 2 plus the acceleration due to gravity multiplied by the height of the inlet minus the mass flow rate at the exit into the enthalpy at the exit plus the square of the velocity at the exit divided by 2 plus acceleration due to gravity multiplied by the height of the exit minus the rate at which work is done by the system. In a steady state process, we assume that the state of the mass or the working fluid at each point, including the inlet and the exit and the control volume, does not vary with time. This means that the total energy within our system doesn't vary with time. This also means that the mass within our control volume does not vary with time. So the mass flow rate at the inlet is equal to the mass flow rate at the exit. Due to these assumptions, we can write our energy equation as this. And dividing both sides by the mass flow rate, we have this. We define dot Q, which is the rate of heat transfer to our system, divided by the mass flow rate, and dot W, which is the rate at which work is done by our system, divided by the mass flow rate, as the heat transfer and work done per unit mass flowing in and out of our control volume. And this is the energy equation with which we analyze steady-state processes. A nozzle is a device that increases the velocity of a fluid while reducing its pressure. A diffuser is a device which increases the pressure of a fluid by reducing its velocity. So nozzles and diffusers perform opposite tasks but work in a similar manner. The rate of heat transfer for a nozzle or diffuser is usually negligible, and no work is usually involved. The change in potential energy is often also negligible. We can therefore write our equation for nozzles and diffusers as the enthalpy at the inlet plus the square of inlet velocity divided by 2 equals the enthalpy at the exit plus the square of exit velocity divided by 2. Air at 10 degrees Celsius and 80 kilopascals enters the diffuser of a jet engine steadily with a velocity of 200 meters per second. The inlet area of the diffuser is 0.4 meters squared, and the air leaves the diffuser with a velocity that is very small compared to the inlet velocity. Determine 1. The mass flow rate of the air, and 2. The temperature of the air leaving the diffuser. Assume air is a perfect gas with the gas constant being 0.287 kilojoules per kg Kelvin and the specific heat at constant pressure 1.005 kilojoules per kilogram Kelvin. So to calculate the mass flow rate, we can use the expression mass flow rate equals velocity multiplied by cross-sectional area divided by specific volume. Now we know the velocity at the inlet, which is 200 meters per second. We also know the cross-sectional area of the inlet, which is 0.4 meters squared, but we don't know the specific volume of the fluid at the inlet. We can use the ideal gas equation, PV equals RT. So rearranging this, we have V equals RT divided by P, which means the specific volume at the inlet is equal to the gas constant multiplied by the temperature at the inlet divided by the pressure at the inlet. We know the pressure at the inlet is 80 kilopascals, and the temperature at the inlet is 10 degrees Celsius or 283 Kelvin. So substituting these values, we can find our specific volume at the inlet, and we get this as 1.015 meters cubed per kg. So using this value, we can calculate our mass flow rate, and we obtain our mass flow rate to be 78.8 kilograms per second. To calculate the temperature of the air leaving the diffuser, we'll use the energy balance equation for a diffuser. We can rewrite this equation as the square of the inlet velocity minus the square of the exit velocity divided by 2 is equal to the enthalpy at the exit minus the enthalpy at the inlet. We know the inlet temperature is 283 Kelvin and the inlet velocity is 200 meters per second. The exit velocity is small compared to the inlet velocity, so it is negligible, and we'll take it as 0 here. Since air is an ideal gas, we can write the equation as the square of the inlet velocity minus the square of the exit velocity divided by 2 equals the specific heat at constant pressure into the exit temperature minus the inlet temperature. So, substituting our known values, we have this. The unit of each term in our energy equation is typically given in kilojoules per kg, but for the velocity terms, we're squaring the meters per second unit. And from dimensional analysis, this corresponds to the joule per kg unit. So to convert this to kilojoules per kg, we divide by 1000. From this, we obtain the exit temperature as 303 Kelvin or 30 degrees Celsius. For our next problem, we have this. Steam at 0.6 megapascals and 200 degrees Celsius enters an insulated nozzle with a velocity of 50 meters per second. It leaves at a pressure of 0.15 megapascals and a velocity of 600 meters per second. Determine the final temperature if the steam is superheated in the final state, and the quality if it is saturated. So we write our equation for the nozzle, and we can determine the initial enthalpy using steam tables. The pressure at the inlet is 0.6 megapascals or 600 kilopascals, and the inlet temperature is 200 degrees Celsius. From the steam tables, we see here that our inlet temperature of 200 degrees Celsius is higher than the saturation temperature, 158.83 degrees Celsius. This means our steam is superheated. From our superheated steam tables, we see that the enthalpy of steam at 0.6 megapascals and 200 degrees Celsius is 2850.6 kilojoules per kg. We can write our exit enthalpy HE as the enthalpy at the inlet plus the square of inlet velocity minus the square of exit velocity divided by 2. And let's not also forget to divide by 1000. So the velocity at the inlet is 50 meters per second, and the exit velocity is 600 meters per second. Using all our values, we obtain the exit enthalpy as 2671.9 kilojoules per kg. We were given the exit pressure as 0.15 megapascals or 150 kilopascals. Checking our steam tables, we see that the enthalpy of saturated vapor at 150 kilopascals is 2693.1 kilojoules per kg. Our exit enthalpy is less than this, meaning that steam at the exit is a saturated liquid vapor mixture. If the enthalpy was greater than Hg, we would consider the steam superheated. So to calculate the dryness fraction, we use H equals Hf plus X HFG. And at 150 kilopascals from our steam tables, Hf equals 467.13 kilojoules per kg, and HFG equals 2226 kilojoules per kg. So using these values in the expression, we obtain our dryness fraction as 0.99.